Hello there, and welcome to Theories Before Sleep. I'm so glad you're here. Maybe it's been a long day, your mind still spinning with worries and tasks. Perhaps you're exhausted but restless, thoughts racing when you need them quiet. Or maybe you're simply curious about the universe, seeking something peaceful to carry you into sleep, a gentle voice in the darkness. Tonight's journey is for you. You don't need to do anything but rest. Let your breath slow, your thoughts soften, and your body grow light. There's nothing to accomplish here, nothing to prove, only wonder to experience. We're going to explore 100 theories about the universe, not in a rush, but slowly, gently. From the smallest particles to the largest cosmic structures, each theory a quiet doorway into mystery. Some will feel familiar, others strange and distant. All are presented to help you drift peacefully towards sleep, carried by curiosity and calm. If these explorations help you unwind, consider liking and subscribing. It helps others find their way here too, one sleepy soul at a time. Now, let's begin. The first theory is waiting, patient and quiet. The universe might be infinite in size, space could stretch forever in all directions, never ending, never reaching a boundary or edge. This theory suggests that if you could travel fast enough and far enough, you would never find a wall, never encounter the end of existence, only more galaxies, more stars, more space extending endlessly. The observable universe has limits only because light has had finite time to reach us since the beginning. But beyond what we can see, reality might continue without bound. An infinite universe would contain infinite matter, infinite possibilities, perhaps even infinite copies of everything that exists here. The mathematics allows for this. The observations don't contradict it. Yet we can never know for certain, never travel far enough to confirm or deny infinity. Some mysteries remain beautifully out of reach, and perhaps that's exactly as it should be. Questions too vast for any answer to contain. The Big Bang might not be the true beginning. The Big Bang marks the earliest moment we can describe with physics, but something might have existed before it. This theory suggests our universe could have emerged from a previous state. Perhaps the collapse of an earlier universe or a quantum fluctuation in a timeless realm. The Big Bang would then be a transition, rather than an absolute beginning, a doorway between states of existence rather than the first moment of time itself. Some models propose an eternal cycle of expansion and contraction, universes being born and dying in endless succession. Others imagine our cosmos budding off from a larger structure, one universe among many in an infinite garden. We cannot see past the Big Bang's brilliant curtain of light and energy. What came before remains hidden, perhaps forever, a mystery that invites wonder rather than frustration, reminding us that even beginnings might have beginnings, origins stretching back into darkness we cannot penetrate. Dark matter might be made of unknown particles. Most of the universe's mass exists in a form we cannot see, touch, or directly detect. This invisible substance, called dark matter, reveals itself only through gravity, bending light and holding galaxies together with its silent pull. The theory suggests dark matter consists of particles unlike anything in our familiar world, perhaps remnants from the universe's earliest moments, existing all around us in vast invisible clouds. These particles might pass through ordinary matter like ghosts through walls, barely interacting with the atoms that make up stars and planets and bodies. Trillions could be flowing through you right now, unfelt and unknown. Scientists search for them in deep underground laboratories, waiting for the rare moment when a dark matter particle might collide with normal matter and reveal itself. Until then, this cosmic majority remains mysterious, the universe keeping its secrets, matter that shapes everything while remaining forever in shadow. Dark energy might be pushing space apart. Something is causing the universe to expand faster and faster, overcoming gravity's pull, driving galaxies away from each other with increasing speed. This mysterious force, called dark energy, makes up most of the universe's total energy, yet we don't know what it is or why it exists. The theory suggests dark energy might be a property of space itself, a kind of cosmic pressure that grows stronger as space expands, creating more of itself as the universe grows. It would mean empty space isn't truly empty, but filled with invisible energy that pushes rather than pulls. This force is gentle, barely noticeable across small distances, but across billions of light years it dominates everything, determining the universe's ultimate fate. The expansion accelerates, galaxies drift apart, and eventually the cosmos might become cold and lonely, stars separated by distances light can never cross. Dark energy whispers of endings written in the fabric of space, inevitable and patient and strange. The universe might be flat in shape. Space itself has geometry, a shape that determines how parallel lines behave and how distances add up across cosmic scales. The theory suggests our universe is flat, meaning Euclidean geometry holds true everywhere. Triangles' angles sum to exactly 180 degrees, and parallel lines never meet or diverge. This flatness emerges from precise measurements of the cosmic microwave background, ancient light that carries information about space's curvature. A flat universe extends infinitely, balanced perfectly between the positive curvature of a sphere and the negative curvature of a saddle. This balance seems improbably exact, suggesting something in the universe's early moments set this geometry with remarkable precision. Alternative theories propose the universe might be slightly curved, too subtly for us to measure, perhaps forming a vast sphere so large its curvature remains invisible. But current evidence points to flatness, space stretching out like an infinite plane, simple and strange and beautiful in its perfect balance. Time might have started with the universe. Before the Big Bang, time itself might not have existed, making the question of what came before meaningless. This theory proposes that time is not eternal, but began with the universe, emerging alongside space and matter and energy. If true, there was no before the beginning, no prior moment from which the universe arose, because moments themselves didn't exist yet. Time would be a property of the universe rather than a container in which the universe sits. This challenges our intuition deeply, since we experience time as fundamental and inevitable, flowing from past to future regardless of what happens within it. But general relativity suggests time is flexible, woven together with space into a single fabric that can bend and stretch. If space began at the Big Bang, perhaps time did too, both springing into existence together. The universe would then be truly self-contained, needing no external stage on which to perform, no prior cause to explain its beginning. The universe might be one of many in a multiverse. Our cosmos could be just one bubble in an infinite foam of universes, each with different properties and laws. This theory, emerging from various branches of physics, suggests that what we call the universe is actually a local region in something far larger and stranger. Other universes might exist beyond our reach, separated by unbridgeable distances or existing in different dimensions entirely. Some might have different fundamental constants, making atoms impossible or gravity too weak to form stars. Others might be similar to ours, perhaps even identical, containing copies of everything we know. The multiverse would be vast beyond comprehension, making our already enormous cosmos seem tiny and provincial. We could never visit these other universes, never confirm their existence through direct observation. They remain theoretical, suggested by mathematics, but invisible to measurement. Yet the possibility lingers, beautiful and unsettling, the idea that we inhabit just one small corner of a reality far stranger and larger than we can imagine. Inflation might have stretched space exponentially. In the universe's first fraction of a second, space itself might have expanded faster than light, growing from smaller than an atom to larger than a galaxy in less time than it takes light to cross a nucleus. This theory, called cosmic inflation, proposes that a special kind of energy caused space to double in size repeatedly, over and over, in an incredibly brief moment. This rapid expansion would explain why the universe appears so uniform, why distant regions that should never have been in contact look eerily similar. It would also explain the universe's flatness, stretching any initial curvature until space became geometrically flat. Inflation would have ended as suddenly as it began, the special energy converting into ordinary matter and radiation, creating the hot, dense state we call the Big Bang. The theory solves several cosmic mysteries elegantly, but we cannot directly observe those earliest moments. Evidence comes from subtle patterns in ancient light, whispers of an event so brief and violent it shaped everything that followed. The universe might be holographic. All the information in our three-dimensional universe might be encoded on a two-dimensional surface, like a hologram projected from a distant boundary. This strange theory suggests that depth is in some sense illusory, that the universe we experience could be a projection from information stored on a cosmic screen we cannot see. The holographic principle emerges from studying black holes and quantum mechanics, where physicists discovered that the information content of a region of space depends on its surface area rather than its volume. If true, everything that happens here, every particle and force and thought, would correspond to data on a distant boundary, perhaps located at the edge of the observable universe. We would be patterns in that information, consciousness emerging from relationships encoded in two dimensions. The theory remains speculative but mathematically compelling, suggesting reality is stranger than it appears, depth and solidity emerging from something fundamentally flat and abstract, like shadows cast by a fire we cannot see. Quantum mechanics might govern the universe's birth. The universe might have emerged from a quantum fluctuation, a random event allowed by the uncertainty principle operating in a realm without space or time. This theory suggests that quantum mechanics, which governs the behavior of particles, might also govern the birth of universes. In quantum theory, pairs of particles constantly pop into existence from nothing, borrowing energy from the vacuum and disappearing almost immediately. If the same process could occur at cosmic scales, a universe might spontaneously emerge, inflating rapidly before quantum effects could pull it back into nothingness. The universe would then be, in a sense, a quantum accident, not designed or caused by anything external but simply allowed by the probabilistic nature of reality. This idea is strange and difficult to test, requiring us to apply quantum mechanics to the entire cosmos. Yet it offers an answer to the deepest question: why is there something rather than nothing? Perhaps because nothing is unstable, and something is what happens when quantum uncertainty operates without constraint. The cosmic microwave background might hold hidden patterns. Ancient light from the early universe fills all of space, carrying information about cosmic history and its subtle temperature variations. This radiation, called the cosmic microwave background, comes from a time when the universe was young and hot, when matter and light were still mixed together in a glowing plasma. As the universe expanded and cooled, this light was released, travelling through space for billions of years until it reaches us now, cooled and stretched into microwave wavelengths. Scientists study this light carefully, looking for patterns that reveal the universe's shape, age, and composition. Some theories suggest hidden patterns might exist in this radiation, anomalies that could point to exotic physics or structures beyond our current understanding. Perhaps the cosmic microwave background contains evidence of other universes colliding with ours, or signatures of cosmic strings, or hints of what happened before the Big Bang. The light is a cosmic fossil, the oldest thing we can observe, and it might hold secrets we haven't yet learned to read. Black holes might connect to other regions of space. The centers of black holes, where gravity becomes infinite and physics breaks down, might not be dead ends but gateways to other places. This theory suggests that the singularities at black holes' hearts could connect to distant regions of space, or even other universes, forming bridges called wormholes. Matter falling into a black hole might not be destroyed but transported elsewhere, emerging from a white hole, a hypothetical object that spews matter out rather than pulling it in. These connections would be incredibly dangerous and unstable, probably collapsing before anything could travel through them, but they might exist briefly in the quantum foam of space-time. If stable wormholes could somehow be created or found, they might allow travel across vast distances instantly, shortcuts through the fabric of space itself. But we have no evidence such passages exist, and the mathematics suggests they would require exotic matter with negative energy to remain open. Black holes keep their secrets, and what happens at their centres remains one of physics' deepest mysteries. The universe might be rotating, space itself could be spinning, carrying galaxies along in a vast cosmic rotation we cannot directly perceive. This theory proposes that the universe has angular momentum, a preferred axis around which everything turns, though the rotation would be incredibly slow, taking billions of years to complete a single revolution. If true, this rotation would have profound implications for our understanding of cosmic structure and the universe's origin. It might explain certain large-scale patterns in galaxy distributions, or create subtle asymmetries in the cosmic microwave background. Detecting cosmic rotation is extremely difficult because we're inside the rotating system, like trying to feel Earth spin while standing on its surface. Scientists look for statistical patterns in galaxy orientations, or subtle distortions in ancient light. Most evidence suggests the universe is not rotating, or if it is, the rotation is too slow to measure. But the possibility remains, the idea that the entire cosmos might be turning slowly in space, a dance too vast and gradual for us to feel. Cosmic strings might thread through space. The universe might contain incredibly thin, incredibly dense defects in space-time, left over from the early universe when forces separated and space underwent dramatic transitions. These cosmic strings, if they exist, would be narrower than an atom but longer than galaxies, stretching across the universe like cracks in frozen ice. They would have enormous mass concentrated in almost no volume, creating intense gravitational fields that could bend light and disturb nearby matter. Cosmic strings might move through space at nearly the speed of light, oscillating and creating gravitational waves as they vibrate. If two cosmic strings intersected, they might exchange partners and reconnect in new configurations, creating loops that would gradually decay, radiating energy into space. We have never directly observed a cosmic string, and they might not exist at all, but certain theories of the early universe predict their formation. They would be fossils from the universe's first moments, scars in space-time that carry information about conditions when the cosmos was unimaginably hot and dense. The universe might have more than three. Spatial dimension space could extend in directions we cannot perceive, hidden dimensions curled up so small that we never notice them in daily life. This theory, emerging from string theory and other attempts to unify physics, suggests that the universe has more than the three dimensions of length, width, and height that we experience. These extra dimensions might be compactified, rolled up into tiny shapes at every point in space, too small for us to enter or explore but influencing physics at quantum scales. Particles might be vibrating strings moving through these higher dimensions, and the different ways they vibrate would appear to us as different types of particles. Forces might propagate through these hidden dimensions, and gravity might seem weaker than other forces because it spreads out into extra dimensions we cannot access. If we could somehow perceive these dimensions, reality would look utterly different, space having structure and complexity we cannot imagine. But they remain theoretical, suggested by mathematics but never observed, dimensions that might exist everywhere while remaining forever invisible. The weak anthropic principle might explain cosmic fine-tuning. The universe's fundamental constants seem precisely calibrated to allow life, and perhaps we observe these values simply because we couldn't exist otherwise. This principle suggests that the universe's properties are not objectively special, but appear special to us, because only universes with these properties can produce observers. If the strong nuclear force was slightly weaker, stars couldn't form. If gravity were slightly stronger, the universe would have collapsed long ago. If the electromagnetic force had a different strength, atoms couldn't bond into molecules. These coincidences seem remarkable, but the anthropic principle offers a simple explanation. We find ourselves in a universe suitable for life, because unsuitable universes have no one to observe them. This doesn't explain why the universe has the properties it does, but it explains why we shouldn't be surprised to find ourselves in a life-permitting cosmos. It's a kind of selection effect, like being surprised that you were born in a time and place where humans can survive. The universe might not be designed for us. We might simply be adapted to the universe we happen to inhabit. The strong anthropic principle might suggest purpose. The universe might be required to develop observers, its properties not merely compatible with life, but somehow aimed at producing consciousness. This stronger version of the anthropic principle suggests that the cosmos has a purpose or direction, that the emergence of awareness is not an accident but an inevitable or necessary outcome. The theory is controversial and borders on philosophy rather than physics, since it implies something like intention in the universe's structure. Some interpretations suggest that observers are necessary for the universe to exist at all, that consciousness collapses quantum possibilities into definite reality, and without observers the universe would remain a blur of potential. Others propose that the universe is part of a larger system that requires observers for some unknown reason, perhaps related to information processing or cosmic evolution. The strong anthropic principle is difficult to test and might not be scientific in the traditional sense, but it addresses deep questions about meaning and purpose, offering the possibility that we are not accidents in an indifferent cosmos, but somehow essential to reality itself. The universe might be cyclic. Cosmic history might repeat endlessly, with each universe ending in a big crunch that becomes the next universe's Big Bang. This cyclic model suggests that expansion and contraction alternate eternally, each cycle lasting trillions of years before collapsing back to a point and bouncing into a new expansion. The universe would have no beginning and no end, only endless repetition, each cycle potentially similar to the last or perhaps subtly different. Between cycles, all matter and energy would be compressed to infinite density, conditions so extreme that the laws of physics might reset, fundamental constants possibly taking new values. Each universe would be born from the death of the previous one, like a phoenix rising from ashes, time flowing in an eternal loop. We could never know what happened in previous cycles, all information erased in the collapse, each universe starting fresh. The cyclic model offers an alternative to the idea of a singular beginning, replacing creation with eternal transformation, the cosmos breathing in and out across timescales that dwarf our comprehension. Vacuum energy might fill empty space. Even in the purest vacuum, devoid of matter and radiation, space itself might contain energy, a kind of cosmic pressure that emerges from quantum fluctuations. This vacuum energy would be a property of space itself, present everywhere, unchanging and eternal. Quantum mechanics predicts that empty space is not truly empty, but filled with virtual particles constantly appearing and disappearing, borrowing energy from the vacuum for brief moments. These fluctuations might create a baseline energy density, a floor below which energy cannot fall. If this vacuum energy is positive, it would cause space to expand, pushing the universe apart, and might be what we observe as dark energy. The calculations are tricky though. Quantum theory predicts vacuum energy should be enormous, far larger than what we observe, a discrepancy so vast it's called the worst prediction in physics. Something about the vacuum must be different from our theories, some cancellation or mechanism we don't understand. Empty space holds mysteries, and what we call nothing might be something stranger than we imagine. The cosmological constant might be fundamental. Einstein introduced a constant into his equations to keep the universe static, then called it his greatest blunder when expansion was discovered, but that constant might actually exist. The cosmological constant represents a fixed energy density in space, a kind of anti-gravity that pushes outward, counteracting matter's gravitational pull. Modern observations suggest the cosmological constant is real and positive, driving the universe's accelerating expansion, making up about 70% of the cosmos's total energy. If the constant is truly fundamental, built into the structure of space-time itself, then the universe's acceleration is permanent and will continue forever. Galaxies will drift apart, stars will burn out, and eventually the cosmos will become cold and dark. Matter spreads so thin that nothing new can form. The cosmological constant determines this fate, a single number that shapes cosmic destiny across trillions of years. Why it has the value it does remains mysterious, one of physics' deepest questions, a constant that seems arbitrary, yet determines everything about the universe's future. Quantum fluctuations in the early universe might have seeded all cosmic structure, tiny variations in density that grew over billions of years into galaxies and clusters. This theory suggests that the universe's large-scale structure originated from quantum uncertainty, random fluctuations in energy that occurred when the cosmos was unimaginably small. Inflation would have stretched these microscopic variations to cosmic scales, freezing them into the fabric of space as permanent density differences. Regions that were slightly denser than average would attract more matter through gravity, growing denser still, while less dense regions would empty out. Over time, these tiny seeds would grow into the cosmic web we observe today, galaxies and clusters connected by filaments of matter, separated by vast voids. The cosmic microwave background shows these primordial fluctuations directly, temperature variations that correspond to density differences in the early universe. From quantum randomness came cosmic order, the largest structures in existence emerging from the smallest possible variations. Chance events at the beginning determining the arrangement of matter across billions of light years. The universe might have magnetic fields on cosmic scales. Vast magnetic fields might thread through intergalactic space, too weak to affect individual particles, but strong enough to influence structure across millions of light years. These cosmic magnetic fields would be generated by currents flowing through ionized gas, creating organized patterns that stretch between galaxy clusters. The fields might have been seeded in the early universe, or generated later by galaxies and black holes, then amplified by cosmic motions over billions of years. They could channel charged particles along specific paths, creating invisible highways through space, and might influence how galaxies form and evolve. Detecting these fields is difficult because they are incredibly weak, requiring careful observations of how light from distant objects is polarized or how radio waves are affected. Some measurements suggest large-scale magnetic fields do exist, while others remain ambiguous. If cosmic magnetism is real, it would add another layer of structure to the universe, invisible forces organizing matter on the larger scales, fields that emerged from the chaos of the early cosmos and now span distances light takes millions of years to cross. Gravitational waves might carry information from the Big Bang ripples in space-time itself, created by violent cosmic events, travel through the universe at the speed of light, and some might come from the very beginning. Gravitational waves were predicted by Einstein, and finally detected in recent years, confirming that massive objects in motion can create waves in the fabric of space. These waves pass through matter without being absorbed, carrying information across cosmic distances unchanged. Some theories suggest gravitational waves were produced during the Big Bang or cosmic inflation, primordial ripples that still travel through space today. If we could detect these ancient waves, they would tell us about conditions in the universe's first moments, times and energies we can never recreate in laboratories. Unlike light, which was trapped in the early universe's hot plasma, gravitational waves could travel freely from the very beginning, making them a unique window into cosmic history. The waves would be incredibly faint, requiring extraordinarily sensitive detectors, but they might be there. Whispers from the universe's birth, information encoded in the stretching and squeezing of space itself. The universe might be electrically neutral. Overall, despite containing vast numbers of charged particles, the cosmos might have exactly equal amounts of positive and negative charge, balancing perfectly to zero. This electrical neutrality is remarkable because nothing in physics requires it, yet observation suggests the universe is neutral to extraordinary precision. If there were even a tiny imbalance, electromagnetic forces would dominate over gravity, and the universe would look completely different. Galaxies would tear themselves apart, stars couldn't form, and matter would be pushed around by electric fields rather than pulled together by gravity. The neutrality might be a fundamental property built into the universe's initial conditions, or it might be a consequence of how particles were created in the early cosmos. For every electron, there's a proton somewhere, charges cancelling across vast distances, maintaining balance. This neutrality is so precise that if it were off by even 1 part in a billion, we would notice dramatic effects. The universe keeps its electrical books perfectly balanced, a cosmic accounting that allows gravity to shape large-scale structure, while electromagnetic forces work at smaller scales. Cosmic voids might not be truly empty. The vast empty regions between galaxy clusters, called cosmic voids, might contain dark matter, diffuse gas, and perhaps structures we haven't yet detected. These voids make up most of the universe's volume, regions spanning hundreds of millions of light years with almost no visible matter. But empty is relative. Dark matter might fill these voids, its gravity too weak to pull normal matter together, but still present in significant amounts. Thin gas might pervade these regions, too sparse to glow, but detectable through its effects on light passing through. Some theories suggest voids might contain galaxies too faint to see, or that they might be expanding faster than the rest of the universe, creating even larger empty regions over time. The voids are shaped by the same forces that created galaxy clusters, just in reverse, matter draining out of these regions and flowing toward denser areas. They're not empty in the absolute sense, but emptier than their surroundings, relative deserts in the cosmic landscape, spaces where matter is sparse and structure is subtle. The universe might have preferred directions. Space might not be perfectly isotropic, meaning it might have properties that vary depending on which direction you look. This would violate one of cosmology's fundamental assumptions, the cosmological principle, which states that the universe looks the same in all directions. Some observations hint at anomalies in the cosmic microwave background, patterns that seem aligned with particular directions in space, sometimes called the axis of evil. These patterns might be statistical flukes, artifacts of how we analyze data, or they might point to real asymmetries in the universe's structure. If space has preferred directions, it could indicate rotation, magnetic fields, or exotic physics from the early universe. It might mean the universe is not as simple and symmetric as we thought, that our corner of the cosmos has special properties or orientations. Most physicists remain skeptical, favouring explanations that preserve isotropy, but the possibility lingers, the idea that space itself might have grain or texture, directions that are fundamentally different from others in ways we're only beginning to detect. Neutrinos might have shaped cosmic structure. These ghostly particles, barely interacting with matter, might have influenced how galaxies formed and where they're located. Neutrinos are incredibly abundant, billions passing through your body every second. But they're so light and weakly interacting that they're difficult to study. In the early universe, neutrinos moved at nearly the speed of light, streaming freely through space while matter was still hot and dense. This motion would have smoothed out density variations on certain scales, preventing structure from forming in some regions while allowing it in others. The effect would be subtle but measurable, influencing the distribution of galaxies across the universe. By studying how galaxies cluster, scientists can infer properties of neutrinos, including their masses, which are still not precisely known. Neutrinos connect the smallest scales of particle physics to the largest scales of cosmology, tiny particles that shaped cosmic structure through their collective behavior. They're everywhere and nowhere, passing through everything, barely noticed yet quietly influential ghosts that help determine where galaxies would form across billions of light years. The universe might be older than we think. Current measurements suggest the universe is about 13.8 billion years old, but some observations hint it might be older. This discrepancy arises from different ways of measuring cosmic age, each with its own uncertainties and assumptions. Observations of the oldest stars suggest they're nearly as old as the universe itself, leaving little time for the first stars to form. Some distant galaxies appear surprisingly mature, as if they've been evolving for longer than the universe's age should allow. These tensions might indicate errors in our measurements or assumptions, or they might point to new physics, something about the universe's expansion or early history that we don't understand. If the universe is older than we think, it would change our understanding of cosmic history, giving more time for structures to form and evolve. The age of the universe is one of cosmology's most fundamental parameters, a number that constrains everything else, and getting it right matters. The mystery remains, measurements pointing in slightly different directions, suggesting either error or new discovery waiting just beyond our current understanding. The cosmic web might be alive with flowing gas. The filaments connecting galaxy clusters might contain rivers of gas flowing between structures, matter streaming along invisible highways in space. This cosmic web, revealed by computer simulations and observations, forms the largest structures in the universe, filaments hundreds of millions of light years long, connecting clusters like threads in a vast tapestry. Gas within these filaments might not be static, but flowing, pulled by gravity from one cluster to another, creating currents that span cosmic distances. These flows would be incredibly slow by human standards, taking millions of years to move significant distances, but they would represent ongoing cosmic circulation, matter redistributing itself across the universe. The flowing gas might feed galaxies, providing raw material for new stars, or it might be stripped from galaxies and expelled into intergalactic space. Detecting these flows is difficult because the gas is hot and diffuse, glowing faintly in wavelengths our eyes can't see. But if they exist, they would make the cosmic web dynamic rather than static, a living structure where matter moves and evolves, the universe breathing through its largest veins. The universe might contain primordial black holes. Black holes might have formed in the early universe, not from collapsing stars but from density fluctuations when the cosmos was young and chaotic. These primordial black holes could have any mass, from smaller than atoms to thousands of times the Sun's mass, depending on when and how they formed. If they exist, they might make up some or all of the dark matter, invisible objects scattered throughout galaxies, influencing cosmic structure through their gravity. Primordial black holes would be difficult to detect directly because they don't emit light, but they might reveal themselves through gravitational lensing, bending light from background objects, or through gravitational waves if they merge with each other. Some theories suggest these black holes could seed the formation of galaxies, providing gravitational anchors around which matter could collect. Others propose they might be rare or non-existent, ruled out by observations that constrain how much mass can be hidden in black holes of various sizes. The idea remains speculative but tantalizing. ancient black holes that might have existed since the universe's first moments, silent witnesses to cosmic history, scattered through space like seeds from the beginning. Cosmic rays might come from exotic sources, the most energetic particles in the universe, travelling at nearly the speed of light, might originate from black holes, colliding galaxies, or even decaying dark matter. These cosmic rays, mostly protons and atomic nuclei, strike Earth's atmosphere constantly, creating showers of secondary particles that rain down on the surface. The most energetic cosmic rays carry more energy than anything we can produce in particle accelerators, and their origins remain mysterious. Supernova explosions can accelerate particles to high energies, but the most extreme cosmic rays seem too energetic for supernova to explain. Perhaps they come from supermassive black holes at galaxy centers, particles accelerated by intense magnetic fields near the event horizon. Or they might be produced by colliding neutron stars, or by the decay of exotic particles left over from the early universe. Cosmic rays arrive from all directions, making it difficult to trace them back to specific sources, and they're deflected by magnetic fields as they travel through space. They carry information about extreme physics, processes that push matter and energy to their limits, mysteries written in particles that cross the universe to reach us. The universe might have topological defects. Space itself might contain knots, twists, or other exotic structures formed during phase transitions in the early universe. These topological defects would be stable configurations of fields, like knots in a rope that can't be untied without cutting the rope. Different types might exist. Monopoles, which are isolated points, cosmic strings, which are one-dimensional lines, domain walls, which are two-dimensional surfaces, and textures, which are more complex configurations. Each type would have different properties and effects on surrounding space and matter. Monopoles might be incredibly massive, warping space-time around them. Domain walls might slice through space, creating boundaries between regions with different properties. Most theories predict these defects should exist if the universe underwent certain kinds of phase transitions, but we've never observed any definitively. They might be extremely rare, diluted by cosmic expansion, or they might not exist at all if the universe's history was different than we imagine. These defects would be scars from the universe's violent youth, permanent marks left by transitions when forces separated and symmetries broke, fossils from times when physics was different than it is today. The expansion might eventually reverse. If dark energy weakens or becomes negative, the universe's expansion could slow, stop, and reverse, leading to a big crunch. This scenario would unfold over trillions of years, giving current structures plenty of time to evolve before the end. As expansion reversed, galaxies would begin moving toward each other rather than apart, their light shifting from red to blue. Over time, the universe would contract, space shrinking, matter becoming denser and hotter. Eventually, galaxies would merge, stars would collide, and the cosmos would become a hot, dense plasma again, conditions approaching those of the Big Bang, but in reverse. Time might continue through the crunch, leading to a bounce and a new cycle of expansion, or time itself might end, all of history compressed back to a point. The Big Crunch is less favoured now than it once was, since observation suggests dark energy is constant or even strengthening, but the possibility remains. The universe's fate depends on the nature of dark energy, a substance we barely understand, and different assumptions lead to different endings, some violent, some gentle, all distant beyond imagining. The universe might end in heat, death, if expansion continues forever. The cosmos will eventually reach maximum entropy, a state of perfect equilibrium where nothing can happen. This heat death would occur in the unimaginably distant future, after all stars have burned out, all black holes have evaporated, and all matter has decayed or been pulled apart by expansion. The universe would become cold, dark, and empty, particles separated by vast distances, no energy available to do work or create structure. Entropy, the measure of disorder, would reach its maximum, and time would lose meaning because nothing would change. The heat death represents not a dramatic ending but a gradual fading. The universe running down like a clock, energy spreading out until it's evenly distributed and useless. Some find this ending depressing, but it's so far in the future that it's almost abstract, trillions upon trillions of years away. By then, everything we know will have long since ended, stars and galaxies mere memories in a cosmos grown old. The heat death is the price of eternal expansion, the universe trading violent collapse for slow, cold dissolution, fading into silence across timescales that dwarf all of history. The universe might experience a big rip. If dark energy strengthens over time, it might eventually overcome all forces holding matter together, tearing apart galaxies, stars, planets, atoms, and even space itself. This dramatic ending, called the Big Rip, would occur in the distant future if dark energy is a certain type called phantom energy, which grows stronger as the universe expands. First, galaxy clusters would be torn apart, individual galaxies separating and drifting into isolation. Then galaxies themselves would dissolve, stars scattered across space. As dark energy strengthened further, solar systems would break apart, planets pulled from their orbits. Eventually, even atoms would be ripped apart, electrons torn from nuclei, and finally space itself would be shredded, the fabric of reality unable to withstand the growing repulsive force. The Big Rip would be violent and complete, everything destroyed in a final crescendo of cosmic expansion. Current observations don't favour this scenario, but they don't rule it out either. The universe's fate depends on how dark energy behaves, and if it strengthens rather than remaining constant, the Big Rip becomes possible, an ending that would erase all structure and return the cosmos to chaos. The observable universe might be tiny compared to the whole. What we can see, limited by the speed of light in the universe's age, might be an infinitesimally small fraction of what exists. The observable universe extends about 46 billion light-years in all directions, a sphere containing everything we can possibly detect. But space might extend far beyond this horizon, perhaps infinitely, containing structures and regions we can never observe because their light hasn't had time to reach us. If the universe is infinite, then the observable portion is literally 0% of the total, a finite bubble in an endless expanse. Even if the universe is finite, it might be vastly larger than what we can see, the observable universe just a tiny patch in a much greater whole. Beyond our horizon, galaxies continue, stars shine, and perhaps other forms of structure exist, all forever hidden from our view. This is both humbling and strangely comforting, the idea that reality extends far beyond our perception, that we inhabit a small corner of something much larger. The universe keeps most of itself secret, and what we call the universe is really just our local neighbourhood, a small sample of a cosmos that might have no end. Quantum entanglement might connect distant parts of space. Particles separated by vast distances might remain connected through quantum entanglement, their properties correlated in ways that seem to transcend space. This phenomenon, verified in laboratories, shows that measuring one particle instantly affects its entangled partner, regardless of the distance between them. Einstein called this spooky action at a distance. Uncomfortable with the implications, but experiments confirm it's real. Some theories suggest entanglement might connect different regions of the universe, creating invisible links across cosmic distances. These connections wouldn't allow faster-than-light communication or violate relativity, but they would mean space is more interconnected than it appears, particles sharing information in ways we don't fully understand. Entanglement might even be related to the structure of space-time itself, some theories proposing that space emerges from quantum entanglement between fundamental degrees of freedom. If true, the fabric of reality would be woven from quantum correlations, distance and separation emerging from patterns of entanglement. The universe would be deeply connected at quantum levels, every part related to every other part through invisible threads, a cosmic web of correlations that underlies the space we perceive. The Planck scale might be where physics changes. At incredibly small distances, about 10 to the minus 35 meters, space and time might become granular or lose meaning entirely. This scale, called the Planck length, represents the limit where quantum effects and gravity become equally important, and our current theories break down. Below this scale, space-time might be foamy, constantly fluctuating, with virtual black holes appearing and disappearing. Or space might be discrete rather than continuous, made of tiny indivisible units like pixels in an image. Time might similarly become granular, flowing in discrete ticks rather than smoothly. At these scales, the concepts of distance and duration might not apply in the usual way, and new physics would be needed to describe what happens. We can never observe the Planck scale directly because it's far smaller than anything we can probe with experiments, but it represents a fundamental limit, a boundary where our descriptions of reality must change. The Planck scale is where quantum mechanics and general relativity meet, and understanding physics at this scale might require a theory of quantum gravity, something physicists have sought for decades but not yet achieved. The cosmological principle might be wrong. The assumption that the universe looks the same everywhere and in all directions might not be true, and we might occupy a special location. This would overturn one of cosmology's foundations, the idea that our position in the cosmos is typical and unremarkable. Some observations hint at anomalies, patterns in the cosmic microwave background that seem to prefer certain directions, or variations in the expansion rate depending on where you look. If the universe is not homogeneous and isotropic, then our theories would need revision, and interpreting observations would become more complex. We might live in a region that's unusually dense or empty, or the universe might have large-scale structure we haven't recognized. Most cosmologists believe the cosmological principle holds, at least approximately, but the possibility of violation remains. If we're not in a typical location, it would raise questions about why, about whether there's something special about our region that allowed life to form. The principle is an assumption, not a proven fact, and challenging it might lead to new understanding, or reveal that the universe is stranger and more varied than we thought. Cosmic acceleration might not be uniform. Dark energy might vary in strength across space or time, making the universe's expansion more complex than current models assume. If dark energy changes, then different regions might expand at different rates, or the expansion might speed up and slow down over cosmic history. This would complicate efforts to measure cosmic distances and understand structure formation. Some theories propose that dark energy is a field that can vary, like a landscape with hills and valleys, and our region of space might be in a particular valley where dark energy has a certain value. Other regions might have different values, leading to different expansion rates. Alternatively, dark energy might evolve over time, starting weak and growing stronger, or vice versa. Detecting such variations is difficult because we can only observe from our specific location and time, but careful measurements of distant supernovae and other cosmic markers might reveal patterns. If dark energy is not constant, it would change our understanding of the universe's fate and history, adding complexity to cosmic evolution and perhaps connecting dark energy to other aspects of physics we don't yet understand. The universe might have no center. In an infinite universe, or even a finite one without boundaries, there's no special point that could be called the center. This is counterintuitive because we're used to objects having centers, but the universe as a whole is different. If space is infinite, then every point is equally valid as a reference, and no location is more central than any other. Even if the universe is finite, it might curve back on itself like the surface of a sphere, which has no center on the surface itself. The Big Bang didn't happen at a point in space, but everywhere simultaneously. Space itself expanding rather than matter moving through space. This means every location can claim to be at the center of the expansion, seeing other galaxies moving away in all directions. The lack of a center is related to the cosmological principle, the idea that the universe is homogeneous and isotropic. It's a strange concept to grasp. The idea that the universe has no privileged location, no center or edge, just space extending in all directions, every point equivalent to every other point, the cosmos without landmarks or boundaries to define a middle. The speed of light might have changed. Some theories propose that the speed of light was different in the early universe, perhaps much faster than it is now. This would have profound implications for cosmology, since the speed of light determines how fast information can travel and how forces propagate. A varying speed of light might explain cosmic horizon problems without requiring inflation, allowing distant regions to come into thermal equilibrium even though they seem too far apart. The theory is controversial because changing the speed of a light affects many other aspects of physics, and it's unclear how such a change would work without violating other principles. Measurements of light from distant galaxies can constrain how much the speed of light could have changed, and so far no clear evidence supports variation. The speed of light is built into the structure of space-time in relativity, and changing it would require modifying fundamental theories. Still, the possibility remains, the idea that one of nature's most fundamental constants might not be constant after all, that the universe's early moments might have operated under different rules, light travelling faster when space was young and hot. The universe might be a simulation. Reality as we experience it might be a computational process running on some substrate we cannot perceive or understand. This idea, popularized by philosophers and physicists, suggests that what we call the physical universe might be information being processed, like a video game or computer simulation. If true, the laws of physics would be the rules of the simulation, and particles and forces would be data structures and algorithms. The simulation might be running on a computer in another universe, or it might be a spontaneous mathematical structure that computes itself. This theory is difficult to test because any evidence we find would itself be part of the simulation, but some have proposed looking for glitches or computational shortcuts that might reveal the underlying structure. The simulation hypothesis raises questions about the nature of reality and consciousness, about whether simulated beings can be truly conscious, and whether our experiences are genuine. It's a modern version of ancient questions about the nature of existence, reframed in computational terms. The universe might be information all the way down, reality emerging from processing rather than existing independently, a cosmic program running for purposes we cannot fathom. The Fermi paradox might indicate we're alone. The apparent absence of alien civilizations in a vast universe might mean intelligent life is extraordinarily rare or faces insurmountable challenges. This paradox, named after physicist Enrico Fermi, asks why we see no signs of extraterrestrial intelligence, despite the billions of stars and planets that should provide opportunities for life. Perhaps life is common, but intelligence is rare, or intelligent life tends to destroy itself before achieving interstellar communication. Maybe space travel is harder than we imagine, or advanced civilizations choose not to communicate, or we're looking in the wrong ways. The silence might indicate that we're among the first intelligent species to arise, or that we're the only ones in our cosmic neighborhood, separated from others by vast distances. Alternatively, aliens might be everywhere but invisible to us, using technologies or communication methods we can't detect. The Fermi paradox is unsettling because it suggests either we're alone, which seems unlikely in such a vast universe, or something prevents civilizations from becoming visible, which raises questions about our own future. The universe remains quiet and we listen, wondering whether the silence means we're unique or simply haven't yet heard the message. The great filter might lie ahead. If intelligent life is rare, something might prevent most species from reaching advanced stages, and we might not have passed this barrier yet. The Great Filter is a hypothetical obstacle that stops civilizations from becoming interstellar, and its location determines humanity's prospects. If the filter is behind us, in our past, then we've already overcome the hardest challenges, and our future is relatively secure. Perhaps the filter was the origin of life itself, or the evolution of complex cells, or the development of intelligence. But if the filter lies ahead, then we face challenges that most civilizations fail to overcome, and our survival is not guaranteed. The filter might be self-destruction through war or environmental collapse, or it might be something we haven't encountered yet, a universal obstacle that appears at certain stages of development. The filter could be technological, biological, or sociological, something about the nature of intelligence or civilization that makes long-term survival difficult. Not knowing where the filter lies makes it hard to assess our chances, and the silence of the cosmos offers no clues. We might be on the verge of passing through, or we might be approaching the barrier that ends most species. Dark flow might indicate external structure. Galaxy clusters might be moving in a particular direction, pulled by something beyond the observable universe's edge. This phenomenon, called dark flow, was controversial when first reported, with some measurements suggesting a large-scale flow of galaxies toward a specific region of sky. If real, dark flow would indicate structure beyond what we can see, perhaps enormous mass concentrations or exotic features left over from before inflation. The motion would be subtle, requiring careful measurement of galaxy velocities and accounting for all known effects. Other studies have failed to confirm dark flow, suggesting it might be a measurement error or misinterpretation of data. If it exists, dark flow would challenge our understanding of cosmic structure and the universe's homogeneity, suggesting that our observable region is influenced by what lies beyond. It might point to a multiverse, with our universe being pulled toward others, or to structures from before the Big Bang that survived into the current era. The debate continues, measurements and analyses pointing in different directions, the possibility of dark flow remaining a tantalizing hint that the universe might be more complex than our models assume. The axis of evil might reveal cosmic asymmetry. Certain patterns in the cosmic microwave background seem aligned with the solar system's geometry, a coincidence that's either meaningless or deeply significant. This alignment, nicknamed the axis of evil, appears in the larger scale temperature fluctuations, which seem to prefer directions related to Earth's orbit and the plane of the solar system. If this is real, and not a statistical fluke, it would violate the cosmological principle and suggest our location is somehow special. Most cosmologists believe the alignment is coincidental, a result of looking at limited data and finding patterns that would disappear with better measurements. But some argue it might point to exotic physics, perhaps cosmic rotation, preferred directions in space, or effects from structures beyond our observable universe. The axis of evil is controversial and not widely accepted, but it represents the kind of anomaly that could either be dismissed as noise or turn out to be the first hint of something profound. The cosmic microwave background is our clearest window into the early universe, and any real patterns in it carry important information about cosmic structure and history. The universe might be flat by coincidence. The universe's geometry appears precisely flat, but this might be an accident rather than the result of inflation or other mechanisms. Flatness requires the universe's density to be exactly at a critical value, balancing expansion and gravity perfectly. Inflation explains this by stretching space until any curvature becomes negligible, but perhaps the universe simply started flat, with no mechanism required. This would be an enormous coincidence, since flatness is an unstable state that requires fine-tuning to maintain. Any deviation from perfect flatness would grow over time, making the universe obviously curved by now, unless it started incredibly close to flat. Some physicists find coincidences unsatisfying, and prefer explanations like inflation that make flatness natural. Others argue that not everything needs explanation, that some aspects of the universe might simply be initial conditions we must accept. The flatness of space is one of cosmology's central observations, a fact that shapes our understanding of cosmic geometry and evolution. Whether it's explained by inflation, by initial conditions, or by something else we haven't thought of remains an open question, one that connects to broader debates about what requires explanation in physics. The multiverse might be unscientific. If other universes are forever beyond our reach, they might not be proper subjects for science, which requires testability and observation. This criticism of multiverse theories argues that science must be grounded in evidence, and claims about unobservable realms are more philosophy than physics. Proponents of multiverse theories counter that the multiverse is a prediction of theories developed to explain observable phenomena, like inflation or string theory, and that predictions don't stop being scientific just because they're hard to test. The debate touches on fundamental questions about what science is and what kinds of explanations are acceptable. Some argue that the multiverse is the best explanation for cosmic fine-tuning, while others say invoking unobservable universes is giving up on finding real explanations. The controversy is unlikely to be resolved soon, since direct observation of other universes seems impossible. But indirect evidence might exist, patterns in the cosmic microwave background or other observations that could only be explained by multiverse effects. The multiverse remains a fascinating and divisive idea, pushing the boundaries of what science can address and raising questions about the limits of human knowledge. The universe might be conscious. Some theories propose that consciousness is not produced by brains, but is a fundamental feature of reality, perhaps present everywhere at some level. This panpsychist view suggests that all matter has some form of experience or awareness, however simple, and that complex consciousness emerges when these basic experiences combine in the right ways. If true, the universe itself might be conscious, not in the sense of having thoughts and intentions like a person, but in possessing some form of awareness or subjectivity. This idea is ancient, appearing in various philosophical and spiritual traditions, but some modern physicists and philosophers take it seriously as a solution to the hard problem of consciousness. If consciousness is fundamental, then it doesn't need to be explained in terms of physical processes, and the combination problem of how simple experiences combine into complex ones becomes the main challenge. The theory is speculative and difficult to test, since we can't directly access other beings' experiences, but it offers a radically different view of mind and matter. The universe might be aware, in its own strange way, reality experiencing itself through countless perspectives, consciousness woven into the fabric of existence rather than emerging from it. The arrow of time might be an illusion. Time seems to flow from past to future, but this might be a feature of our perspective rather than a fundamental property of reality. The laws of physics, at their most basic level, don't distinguish between past and future, working equally well in either direction. The arrow of time emerges from entropy, the tendency of systems to become more disordered, but entropy itself might be a statistical concept rather than a fundamental law. In a large enough universe, or a multiverse, there might be regions where entropy decreases and time appears to run backward. From those regions' perspectives, their past would be our future. The arrow of time might be local and contingent, a feature of our corner of the universe but not universal. Some theories propose that time is more fundamental than space, that temporal flow is built into reality, while others suggest time is emergent, arising from timeless quantum states. The nature of time remains one of physics' deepest mysteries, a concept so familiar yet so poorly understood. We experience time as flowing, as having direction and irreversibility. But whether this flow is real or illusory, fundamental or emergent, remains uncertain, a question that touches on the very nature of existence and change. The universe might be deterministic. Every event might be the inevitable result of prior conditions with no true randomness or free will, the future entirely determined by the past. This view, called determinism, suggests that if you knew the exact state of the universe at any moment and all the laws of physics, you could predict everything that would happen afterward. Quantum mechanics complicates this picture by introducing apparent randomness, but some interpretations, like the many worlds interpretation, restore determinism by saying all possible outcomes occur in different branches. If the universe is deterministic, then your choices, thoughts, and actions are all predetermined by the arrangement of atoms at the Big Bang, and free will is an illusion. This idea is unsettling to many people, but it's also strangely peaceful, suggesting that everything unfolds according to natural law, without arbitrary chance or intervention. Determinism doesn't mean we can predict the future, since we can never know the exact state of anything, but it means the future is in principle determined, already written in the present moment. The universe would be like a vast machine, each part moving according to fixed rules, the whole system evolving from its initial conditions toward whatever future those conditions necessitate. Quantum mechanics might allow. Backward causation effects might precede causes in quantum systems, with future events influencing the past in subtle ways. This strange possibility emerges from certain interpretations of quantum mechanics, and from experiments showing that measurements can retroactively affect earlier states. In the delayed choice quantum eraser experiment, a decision made after a particle has been detected seems to determine what kind of path the particle took, as if the future measurement reached back to influence the past. This doesn't allow sending information backward in time or creating paradoxes, but it suggests that causation in quantum mechanics might be more complex than the simple past-to-future flow we're used to. Some interpretations of quantum mechanics, like the transactional interpretation, explicitly incorporate backward-in-time influences, with waves travelling both forward and backward to create the observed correlations. If backward causation is real, it would challenge our understanding of time and causality, suggesting that the future is not entirely open and the past not entirely fixed. The universe might be a four-dimensional structure where past, present, and future are all equally real, and influences flow in both temporal directions, creating the patterns we observe in experiments. The quantum vacuum might be the ground of reality, the lowest energy state of quantum fields, usually called empty space, might be the most fundamental thing that exists, with particles being excitations of this vacuum. In quantum field theory, what we call particles are really ripples or vibrations in underlying fields that fill all of space. The vacuum is not nothing but a seething sea of virtual particles and fluctuations, the ground state from which all matter and energy emerge. This vacuum might be the closest thing to true nothingness, yet it's not empty, possessing energy and structure and the potential to create particles. Some theories suggest the vacuum might have different possible states, and our universe exists in one particular vacuum state, while other regions might be in different states with different properties. Transitions between vacuum states might have occurred in the early universe, or might occur in the future, potentially changing the laws of physics. The quantum vacuum is strange and subtle, neither something nor nothing, a concept that challenges our intuitions about existence. It might be the foundation of reality, the substrate from which everything else arises, the closest we can come to understanding what nothing means in a quantum universe. The measurement problem might require new physics. Quantum mechanics describes reality as existing in superposition until measured, but what counts as measurement and why it causes collapse remains mysterious. This measurement problem is one of quantum theory's central puzzles, the question of how definite reality emerges from quantum possibilities. Different interpretations offer different answers. Copenhagen says measurement causes collapse, but doesn't explain what measurement is. Many Worlds says there's no collapse, just branching into different realities. Objective collapse theories propose that collapse is a real physical process triggered by certain conditions. The problem touches on the relationship between consciousness and physics, since some interpretations suggest observers play a special role. If consciousness causes collapse, then mind would be fundamental to reality, not reducible to physics. If collapse is objective, triggered by decoherence or gravity, then consciousness is irrelevant to quantum mechanics. The measurement problem might require entirely new physics, a deeper theory that explains both quantum and classical behavior without the awkward divide between them. Or it might be a problem of interpretation rather than physics, a question of how we think about quantum mechanics rather than what the math predicts. The mystery remains, and every physicist has their own preferred interpretation, none provable, all consistent with observations. Decoherence might explain classical reality. The quantum world becomes classical not through mysterious collapse, but through interactions with the environment that destroy quantum coherence. This process, called decoherence, occurs when a quantum system becomes entangled with its surroundings, spreading quantum information into the environment where it becomes effectively irretrievable. As more and more environmental particles become correlated with the system, the quantum superposition becomes practically unobservable, and the system appears to be in a definite classical state. Decoherence happens incredibly quickly for macroscopic objects, explaining why we never see cats in superpositions of alive and dead. The quantum behavior is still there in principle, but it's hidden in correlations with countless environmental particles, making interference effects impossible to observe. Decoherence doesn't solve the measurement problem completely, since it doesn't explain why we observe one particular outcome rather than another, but it shows how classical behavior emerges from quantum mechanics without needing to invoke consciousness or mysterious collapse mechanisms. The boundary between quantum and classical is not fundamental but practical, determined by how well a system is isolated from its environment, and everything is ultimately quantum, just appearing classical when entangled with enough other particles. The EPR paradox might reveal non-locality. Einstein, Podolsky, and Rosen argued that quantum mechanics must be incomplete because it predicts spooky action at a distance, but experiments show the spookiness is real. The EPR paradox demonstrated that quantum mechanics allows particles to be correlated in ways that seem to require instantaneous influences across space, violating locality, the principle that objects are only affected by their immediate surroundings. Einstein hoped this meant quantum mechanics was missing something, that there were hidden variables determining outcomes locally. But Bell's theorem and subsequent experiments showed that no local hidden variable theory can reproduce quantum predictions, meaning either locality or realism must be abandoned. Most physicists accept that quantum mechanics is non-local, that measuring one particle really does instantaneously affect its entangled partner, regardless of distance. This doesn't allow faster-than-light communication because the correlations only appear when results are compared, but it means the universe is more connected than classical physics suggested. Non-locality is a fundamental feature of reality, particles sharing information in ways that transcend space, the universe maintaining correlations across cosmic distances through quantum entanglement, a connectedness that defies our intuitions about separateness and independence. The holographic principle might apply to the universe. Information about the universe might be encoded on its boundary, with our three-dimensional reality being a projection from a two-dimensional surface. This principle, developed from studying black holes, suggests that the maximum information in any region of space is proportional to the surface area of that region, not its volume. If applied to the entire universe, it would mean all the information about everything that happens here is somehow stored on a distant boundary, perhaps at the cosmic horizon. We would be, in a sense, holograms, three-dimensional images projected from two-dimensional data. This doesn't mean we're not real, but it suggests that reality has fewer fundamental degrees of freedom than it appears, that the third dimension might be emergent rather than fundamental. The holographic principle connects quantum mechanics, gravity, and information theory in deep ways, and it's led to new approaches to quantum gravity. If the universe is holographic, then space itself might be an illusion, a useful description that emerges from more fundamental two-dimensional physics. The principle remains speculative when applied to cosmology, but it's well established for black holes, and it hints that reality's structure might be stranger than we imagine, depth emerging from flatness through processes we're only beginning to understand. Black hole, information might be preserved. Information falling into black holes might not be destroyed but encoded on the event horizon or released through Hawking radiation. This question has driven decades of debate among physicists, since quantum mechanics requires information to be conserved, but general relativity suggests anything crossing a black hole's horizon is lost forever. Hawking's discovery that black holes radiate and eventually evaporate made the problem acute. If a black hole evaporates completely, where does the information go? Some theories propose that information is encoded in subtle correlations in the Hawking radiation, retrievable in principle though not in practice. Others suggest the information is stored on the event horizon, the black hole's surface, where it might be accessible to external observers. Recent work on the holographic principle and quantum gravity suggests information is never truly lost, that it's preserved in ways we don't fully understand, but that become clear in a complete theory of quantum gravity. The resolution of the information paradox might require rethinking what happens at event horizons or what black holes really are. The paradox connects deep questions about entropy, information, and the relationship between quantum mechanics and gravity, and solving it might reveal fundamental truths about the universe's structure. The singularity at the Big Bang might be avoidable. The infinite density and temperature predicted at the universe's beginning might be artifacts of incomplete theory, rather than real features of nature. General relativity predicts that if you trace the universe's expansion backward, you reach a point where density and temperature become infinite, a singularity where physics breaks down. But singularities often indicate that a theory is being pushed beyond its limits, not that reality actually becomes infinite. Quantum mechanics might prevent the singularity, providing a minimum size or maximum density, beyond which different physics applies. Some theories propose that the universe bounced from a previous contracting phase, never reaching infinite density. Others suggest that quantum effects smooth out the singularity, replacing it with a finite but extremely dense state. Loop quantum cosmology, for example, predicts that quantum geometry prevents the universe from collapsing to a point, causing it to bounce instead. If the singularity is avoidable, then the Big Bang might not be a true beginning but a transition, and the universe might have a history extending before the Big Bang. The singularity represents the limits of our current theories, a point where we need quantum gravity to proceed, and resolving it might reveal what actually happened at the universe's earliest moment. Space and time might be emergent. The fabric of space-time might not be fundamental, but might emerge from something more basic, perhaps quantum entanglement or information. Some approaches to quantum gravity suggest that space and time are not the fundamental arena in which physics happens, but are themselves physical systems that arise from deeper structures. In this view, space-time is like temperature or pressure, a macroscopic property that emerges from microscopic degrees of freedom. The fundamental theory might be formulated without reference to space or time, with these concepts appearing only in certain limits or approximations. Quantum entanglement might be the basic ingredient from which space is built, regions of space being connected because the underlying quantum states are entangled. Time might emerge from the way quantum states evolve or from thermodynamic processes that define a direction. If space-time is emergent, then the Big Bang might not be the beginning of time but the beginning of the space-time description, and there might be a more fundamental story to tell about what happened. Emergence of space-time would profoundly change our understanding of reality, suggesting that the stage on which physics plays out is itself part of the play, arising from actors we haven't yet identified. The cosmological constant problem might require new symmetries. The observed value of dark energy is vastly smaller than quantum theory predicts, a discrepancy that might point to new physics. Quantum field theory predicts that empty space should have enormous vacuum energy, but observations show that dark energy is incredibly tiny, about 120 orders of magnitude smaller than predicted. This is sometimes called the worst prediction in physics, and it suggests something is wrong with our understanding. Perhaps there's a symmetry or mechanism that cancels most of the vacuum energy, leaving only a tiny residual amount. Some theories propose supersymmetry, which pairs every particle with a partner whose contributions to vacuum energy cancel. But supersymmetry would need to be broken in just the right way to leave a small positive cosmological constant. Other approaches suggest that what we observe as dark energy is not vacuum energy at all, but some other field or effect. The problem might also indicate that our understanding of gravity is incomplete, that general relativity needs modification at cosmological scales. Solving the cosmological constant problem might require revolutionary new ideas, perhaps connecting quantum mechanics and gravity in ways we haven't imagined, or revealing new principles that constrain how energy behaves in the vacuum. The anthropic principle might be unavoidable. Some properties of the universe might be explainable only by noting that we exist to observe them, a reasoning that makes many physicists uncomfortable. The anthropic principle comes in weak and strong forms, but both rely on the idea that our existence constrains what we can observe about the universe. If the universe's constants were different, we wouldn't be here to wonder about them, so we shouldn't be surprised to find ourselves in a universe compatible with life. This reasoning can explain apparent fine-tuning without invoking design or purpose. In a multiverse with varying constants, observers will only arise in regions where conditions permit, and those observers will naturally find themselves in life-permitting universes. Critics argue that anthropic reasoning is unscientific, that it gives up on finding real explanations and settles for "because we're here." Proponents counter that it's simply acknowledging an important selection effect, and that some questions might have no deeper answer. The debate continues, with some physicists embracing anthropic explanations and others rejecting them. The principle might be unavoidable for certain questions, or it might be a temporary placeholder until we find better theories, a way of acknowledging our ignorance while admitting that observer selection plays a role in what we can discover about reality. The universe might contain closed time-like curves. General relativity allows solutions where time loops back on itself, creating paths through space-time that return to their starting point. These closed time-like curves would permit time travel to the past, at least in principle, though they require exotic conditions like rotating black holes or wormholes with negative energy. If such curves exist, they raise paradoxes. What happens if you travel back and prevent your own birth? Some physicists argue that quantum mechanics or unknown physics prevents closed time-like curves from forming, that the universe protects itself from paradoxes through some cosmic censorship. Others suggest that time travel is possible, but paradoxes are avoided through consistency. If you travel back, you become part of the past that always was, unable to change anything. The many worlds interpretation offers another resolution. Travelling back creates a new timeline, so you can't change your own past but can affect an alternate version. Closed time-like curves remain theoretical, never observed, possibly impossible, but they're allowed by our best theory of gravity, suggesting that time might be stranger than we think. The universe might contain loops and tangles in time, regions where past and future meet, causality becoming circular rather than linear, though we may never encounter such places. Quantum tunneling might allow universe creation. The universe might have tunneled into existence from nothing, borrowing energy from the quantum vacuum and repaying it through expansion. Quantum tunneling allows particles to pass through barriers they shouldn't classically be able to cross, appearing on the other side without having the energy to traverse the barrier. If the same process can occur at cosmic scales, a universe might tunnel from a state of zero size and zero energy to a state of finite size, with the energy needed to create matter and radiation being balanced by negative gravitational energy. The universe would then be a quantum fluctuation that grew large enough to become classical, a bubble of space-time that inflated from nothing. This process wouldn't violate conservation of energy because the universe's total energy might be zero, positive energy of matter balanced by negative energy of gravity. Quantum tunneling is well established at particle scales, but applying it to universe creation is speculative, requiring quantum gravity and making assumptions about what nothing means. If the universe did tunnel into existence, then creation would be a natural quantum process, not requiring external causes or agents, reality spontaneously appearing because quantum mechanics allows it, something emerging from nothing through the strange logic of quantum uncertainty. The fine structure constant might vary. This dimensionless number, which characterizes the strength of electromagnetic interactions, might not be constant across space or time. The fine structure constant, about 1/137, determines how strongly charged particles interact, and it appears throughout physics. Some theories suggest it might have been different in the early universe, or might vary in different regions of space. Observations of distant quasar light can constrain how much the constant has changed over cosmic time, looking for tiny shifts in spectral lines that would indicate different electromagnetic strength. Most measurements show no variation, but a few claim to detect small changes, sparking controversy. If the fine structure constant varies, it would indicate that what we call fundamental constants are actually fields that can change, and this would require extending the standard model of particle physics. Variable constants would also affect interpretations of fine-tuning, since a constant that varies might naturally scan through different values in different regions, making our observed value less special. The question remains open, measurements pushing toward better precision, trying to determine whether this fundamental number is truly constant or whether it hides subtle variations that could reveal new physics operating at the deepest levels. The Higgs field might be metastable. The field that gives particles mass might exist in a false vacuum, stable now but potentially able to decay to a lower energy state. If the Higgs field is metastable, then our universe exists in a temporary configuration, and a quantum fluctuation could trigger a transition to the true vacuum. This transition would propagate at the speed of light, a bubble of new vacuum expanding and converting everything it touches to a different state where physics is different. Particles might have different masses, atoms might not be stable, and all structure would be destroyed. The transition might have already started somewhere in the universe, a bubble of true vacuum expanding toward us, though we wouldn't see it coming until it arrived. Calculations based on measured Higgs and top quark masses suggest the Higgs vacuum might indeed be metastable, but the decay time could be much longer than the universe's age, making the threat theoretical rather than immediate. The metastability of the Higgs field connects to questions about vacuum energy and the cosmological constant, and it suggests that our universe might be living on borrowed time, existing in a state that's stable enough to last billions of years, but not truly the lowest energy configuration. Reality might be fragile, held together by quantum barriers that could someday fail. The multiverse might have a measure problem. If infinitely many universes exist, comparing their properties or making predictions becomes mathematically problematic, requiring a way to weigh infinities. The measure problem arises in eternal inflation and other multiverse scenarios where infinitely many regions have different properties. To calculate probabilities, we need to count how many universes have certain features, but with infinities, the answer depends on how you count. Different measures, different ways of comparing infinite sets, give different predictions, and there's no obvious principle for choosing the right measure. This makes the multiverse difficult to test, since predictions depend on arbitrary choices about how to handle infinities. Some physicists argue this makes the multiverse unscientific, while others work on developing natural measures based on physical principles. The measure problem is technical but important, determining whether multiverse theories can make testable predictions or remain forever ambiguous. It connects to deep questions in probability, mathematics and philosophy, asking how we should reason about infinite ensembles and what it means for something to be typical in an infinite collection. The problem might be solvable with better understanding of quantum gravity and cosmology, or it might indicate fundamental limits to what we can predict in a universe with infinite variety. The quantum vacuum might have structure. Empty space might not be a featureless void, but might have texture, grain, or organization at scales too small to observe. Some theories of quantum gravity, like loop quantum gravity, predict that space is made of discrete units, a granular structure at the Planck scale. Other approaches suggest the vacuum might be a condensate, a coherent quantum state like a superfluid, with excitations corresponding to particles and forces. If the vacuum has structure, it might affect how particles behave at high energies or in extreme conditions. The structure might be related to dark energy, the vacuum's properties determining how fast the universe expands. Testing these ideas is difficult because the relevant scales are far beyond current experiments, but indirect effects might be observable in precision measurements or cosmological observations. The vacuum might also have topological features, knots or twists that can't be smoothed out, and these might affect physics in subtle ways. Understanding the quantum vacuum is crucial for quantum gravity and for explaining why the universe has the properties it does. The vacuum might be the key to unifying quantum mechanics and general relativity, the place where these theories meet and where new physics must emerge to resolve their contradictions. The universe might be bouncing eternally. Instead of beginning with a big bang and ending in heat death or collapse, the universe might cycle eternally between expansions and contractions. This bouncing cosmology replaces the initial singularity with a bounce from a previous contracting phase, and it might continue bouncing forever, each cycle lasting trillions of years. The bounces would occur when quantum effects prevent the universe from collapsing to a singularity, causing it to rebound and expand again. Each cycle might be similar to the last, or conditions might change slightly, leading to different physics or structures in each iteration. Bouncing cosmologies solve the initial singularity problem and avoid the need for a beginning of time, but they face challenges in explaining how entropy is reset between cycles and how the universe avoids heat death. Some models propose that the universe grows slightly with each bounce, never quite returning to its previous minimum size, so that time has a direction even though expansion repeats. The bouncing universe is an ancient idea, appearing in various philosophical and religious traditions, and modern physics has given it new mathematical formulations. Whether the universe actually bounces remains unknown, but the possibility offers an alternative to creation ex nihilo, a cosmos that has always existed and always will, cycling through endless transformations. The observable universe might be atypical. Our region of space might have unusual properties compared to the universe as a whole, making our observations misleading. If the universe is infinite or very large, then different regions might have different properties, and we might happen to live in an unusual area. This would affect our understanding of cosmology, since we assume our observations are representative of the whole universe. Perhaps our region is unusually dense or empty, or the expansion rate here differs from the average. If so, then measuring the Hubble constant or dark energy density locally would give values that don't apply elsewhere. Some anthropic reasoning suggests we should expect to live in a typical region where observers can arise, but typicality is hard to define in an infinite universe. We might be in a rare fluctuation, a bubble with special properties embedded in a larger cosmos that looks different. Testing whether we're typical is difficult because we can only observe our local region, but inconsistencies between different measurements might hint that our assumptions are wrong. The possibility that we are atypical is unsettling because it undermines the cosmological principle and makes extrapolating from local observations to cosmic conclusions uncertain. We assume we're typical out of necessity, but the universe might be more varied than we realize, our neighborhood not representative of the whole. The universe might contain domain walls. Phase transitions in the early universe might have created boundaries between regions with different vacuum states, walls that stretch across cosmic distances. These domain walls would be surfaces where the Higgs field or other fields take different values, and crossing a wall would mean entering a region with different physics. The walls would have enormous energy density and would affect the expansion of the universe, either dominating cosmic evolution or being diluted by inflation. If domain walls exist today, they would be visible through their gravitational effects, distorting light and creating patterns in the cosmic microwave background. Most observations suggest domain walls don't exist in our observable universe, but they might exist beyond our horizon, or they might have formed and then been destroyed by cosmic evolution. Domain walls are predicted by some theories of particle physics, especially those involving spontaneous symmetry breaking, and their absence constrains which theories can be correct. If they do exist somewhere, they would be cosmic monuments to the universe's history, boundaries between realms where different possibilities were realized, walls that divide reality into regions with distinct identities, each side living under different rules. Cosmic inflation might be eternal. Once inflation starts, it might never completely end, continuing forever in some regions while stopping in others. This eternal inflation creates a fractal structure, bubbles of slow-roll inflation ending and creating universes like ours, while the space between bubbles keeps inflating, creating more bubbles endlessly. Each bubble would be a universe with potentially different properties, and the collection of all bubbles would form a multiverse of staggering diversity. Eternal inflation naturally leads to a multiverse where all possible outcomes of quantum events are realized somewhere, making the multiverse not just possible, but inevitable. The process would have no end, inflation continuing into the infinite future, always creating new universes faster than existing ones age. This scenario solves some problems, like explaining fine-tuning through anthropic selection, but creates others, like the measure problem of how to count infinitely many universes. Eternal inflation is a prediction of many inflation models, not an additional assumption, and it's difficult to avoid once inflation starts. If true, then our universe is just one bubble in an infinite foam, and most of reality consists of eternally inflating space, a cosmic factory that never stops producing new universes, each one a separate experiment in physics and cosmology. The universe might have magnetic monopoles. Particles with only one magnetic pole, north or south, might exist despite never having been observed. Magnetic monopoles are predicted by many grand unified theories, which attempt to unify the electromagnetic, weak and strong forces. These monopoles would be incredibly massive, perhaps as heavy as bacteria, and they would have been produced in the early universe during phase transitions. If they exist, they're extraordinarily rare, diluted by cosmic expansion or confined to regions we can't access. Monopoles would be stable, unable to decay, and they would interact with magnetic fields in distinctive ways. Detecting them would confirm grand unified theories and reveal new aspects of particle physics. Experiments have searched for monopoles in cosmic rays, in ancient rocks, and in particle accelerators, but none have been found. Their absence is actually a problem for some theories, which predict they should be common. Inflation might solve this by diluting monopoles to undetectable levels, explaining why we don't see them even if they exist. Monopoles would be relics from the universe's earliest moments, fossils from times when forces were unified, and finding even one would be a major discovery, opening windows into physics at energies far beyond what we can produce artificially. The cosmological constant might be anthropic. Dark energy's value might be explained by noting that only universes with small positive cosmological constants can support life. If the cosmological constant were much larger, the universe would expand too fast for galaxies to form. If it were negative, the universe would recollapse before stars could evolve. Only a narrow range of values permits the slow, steady expansion needed for structure formation and life. In a multiverse where different regions have different cosmological constants, observers will only arise in regions with suitable values, and we shouldn't be surprised to find ourselves in such a region. This anthropic explanation is controversial because it doesn't predict the exact value, only that it should be in the life-permitting range, and it requires accepting the multiverse as real. Some physicists find this unsatisfying, preferring explanations that predict the cosmological constant from fundamental principles. Others argue that anthropic reasoning might be the only way to explain certain features of the universe, that not everything has a deeper explanation, and that observer selection is a real effect that must be considered. The debate reflects different views about what constitutes a satisfactory scientific explanation, and whether anthropic reasoning is a legitimate tool or a sign that we've given up on finding real answers. The universe might be a quantum computer. Reality might be fundamentally computational, with physical processes being calculations and the universe's evolution being the execution of a cosmic algorithm. This view, emerging from quantum information theory, suggests that information is more fundamental than matter or energy, and that physics is the study of how information is processed. Quantum mechanics naturally describes information processing, with quantum states being information and evolution being computation. If the universe is a quantum computer, then space and time might emerge from information theoretic principles, and the laws of physics might be algorithms that the universe runs. This perspective has led to new approaches to quantum gravity and to insights about black holes and cosmology. It suggests that the universe's complexity is limited by how much information it can process, and that there might be fundamental limits to computation built into the structure of space-time. The computational view doesn't necessarily mean the universe is a simulation running on external hardware, but rather that computation is the right language for describing physical reality. Information might be the currency of existence, the basic stuff from which everything else is made, and understanding how the universe computes might be the key to understanding why it has the laws and properties it does. The Planck era might hold all answers. The universe's first 10 to the minus 43 seconds might contain the key to understanding everything, but this era is beyond our current ability to describe. During the Planck era, quantum effects and gravity were equally important, and space-time itself might have been quantum, fluctuating wildly without definite geometry. The four forces might have been unified, and particles as we know them might not have existed yet. Understanding this era requires a theory of quantum gravity, which we don't yet have, but it's where the universe's initial conditions were set, where the seeds of all structure were planted. If we could understand the Planck era, we might know why the universe has the properties it does, why the constants have their values, why there's something rather than nothing. The era is forever hidden behind the Planck wall, a barrier of energy and density beyond which our theories break down, but its effects echo through all of cosmic history. The Planck era is where physics becomes most fundamental and most mysterious, where quantum mechanics and general relativity must merge, where time and space might not have existed yet, or might have been very different from what they became. It's the ultimate origin story, the moment when everything began, but it remains beyond our reach, perhaps forever, a time we can speculate about but never directly observe or fully understand. The universe might be fractal structure, might repeat at different scales, with the universe showing similar patterns from the smallest to the largest sizes. This fractal hypothesis suggests that the cosmic web of galaxies and clusters might be part of a self-similar pattern that continues to larger scales beyond what we can observe. Fractals are mathematical objects that look similar at all magnifications, and some observations hint that galaxy distributions have fractal properties. If the universe is truly fractal, it would challenge the cosmological principle, which assumes the universe becomes smooth at large scales. Fractals would mean there's no scale at which the universe is homogeneous, that structure continues indefinitely, clustering within clustering within clustering. Most cosmologists believe the universe becomes homogeneous above a certain scale, around 100 million light-years, but some argue for fractal structure extending further. The question is difficult to resolve because we can only observe a finite region, and fractals can appear smooth if you don't look at large enough scales. If the universe is fractal, it would be strange and beautiful, reality repeating itself across scales, patterns within patterns extending to infinity, the cosmos showing the same face whether viewed through microscopes or telescopes, small and large connected by mathematical symmetry. The vacuum might decay. Catastrophically. The quantum vacuum might be metastable, and a random fluctuation could trigger a transition to a lower energy state, destroying everything. This vacuum decay would start at a point and expand at the speed of light, a bubble of true vacuum growing and converting false vacuum to true as it spreads. Inside the bubble, physics would be different. Particles might have different masses or not exist at all, and all structure would be destroyed. The bubble wall would be a moving boundary between our world and the new one, and we wouldn't see it coming until it arrived, travelling at light speed. Once started, the decay would be unstoppable, spreading until it consumed the entire universe or met other bubbles. The probability of decay depends on the shape of the potential energy landscape, and current measurements suggest our vacuum might be metastable, but with a decay time much longer than the universe's age. This means we're probably safe, but there's a tiny chance that vacuum decay could begin at any moment, anywhere in the universe. It's an existential threat we can do nothing about, a cosmic sword hanging over reality. The possibility that the universe itself is temporary, existing in a state that's stable enough for now but ultimately doomed to transform into something else, erasing everything in the process. The universe might be listening. We close our journey through these theories with a thought that's more poetry than physics, more wonder than mechanism. The universe might be listening, in some strange sense, aware of itself through us. Every question we ask, every theory we propose, every observation we make is the cosmos examining itself, reality becoming conscious of its own existence. We are not separate from the universe, but part of it, matter arranged in patterns that can think and wonder and question. When we look at stars, the universe is looking at itself. When we ponder its origins, the cosmos is contemplating its own birth. This is not a scientific theory, but a perspective, a way of seeing our place in reality that dissolves the boundary between observer and observed. We are the universe's way of knowing itself, consciousness emerging from matter to reflect on matter, awareness arising from the void to wonder at the void. The theories we've explored tonight are humanity's love letters to existence, our attempts to understand the vast mystery we find ourselves within. And perhaps the universe appreciates being understood, being noticed, being loved. Perhaps in our curiosity and wonder, we fulfill some cosmic purpose, not assigned by any designer, but emerging naturally from the universe's own nature. We are the cosmos made conscious, and in our dreams tonight, the universe dreams of itself, resting in the questions it has learned to ask. And so, our quiet journey through the universe comes to a gentle close. We've travelled far tonight, from quantum foam to cosmic voids, from the universe's beginning to its possible endings, touching on questions that span all of space and time. The theories behind us now, like stars fading into dawn, their light still travelling but growing dim as sleep approaches. Some theories offered answers, others only deeper questions, and many dissolved into beautiful uncertainty. Some felt solid, grounded in mathematics and observation, while others shimmered like mirages at the edge of knowledge. But all of them carried a piece of humanity's endless curiosity, our refusal to accept the cosmos at face value, our need to wonder and question, and reach beyond what we can touch. These theories, some ancient and some born yesterday, represent our attempts to understand why there is something rather than nothing, why the universe has the properties it does, why we exist to ask these questions at all. Theories are strange things, aren't they? They're not quite facts, not quite fantasies, but something in between, living in the space between what we know and what we imagine. They're humanity's way of reaching toward truth with imperfect hands, building bridges across chasms of ignorance with nothing but mathematics and observation and hope. Some will be proven right, vindicated by future experiments or observations. Others will fade, replaced by better ideas, better explanations. But the reaching itself, the wondering, never stops. The human mind forever pushing against the boundaries of knowledge, forever asking why and how and what if. If your eyes are already heavy, that's just fine, perfect even. Let the last traces of cosmic mysteries fade behind your thoughts, becoming less distinct, less important with each breath. Let quantum fluctuations and dark energy and multiverses drift away like morning mist, dissolving into the peaceful darkness behind your eyelids. Your breath carries you softly now, each exhale releasing a little more tension, each inhale drawing you deeper into calm, deeper into rest. There's still so much more to discover, endless theories waiting in the vast library of human knowledge, but for now, you've learned enough, wondered enough, travelled far enough through mysteries and questions. The universe can wait until morning, patient and unchanging, ready whenever you return to explore its secrets again. You don't need to remember any of this, not the names of theories, not the details of mechanisms, not even the questions we asked. They were never meant to be memorized, only experienced, like watching clouds drift across the sky or listening to rain fall on a roof. What matters is not what you retain, but how you felt while listening, the gentle stimulation of curiosity, the soft pleasure of learning, the quiet comfort of questions asked in darkness. That's enough. That's everything. The theories were companions for your evening, voices in the dark offering wonder and distraction, helping your mind transition from the day's concerns to the night's rest. Notice how your body has grown heavier as we've talked, how your muscles have softened and relaxed, how even the weight of your thoughts has decreased, becoming lighter, easier to let go. This is the natural rhythm of rest, the way consciousness gradually releases its grip on awareness, letting you drift into sleep like a boat slipping its moorings and floating downstream. You don't need to force it, don't need to try or struggle or make anything happen. Just allow it, the way you'd allow yourself to float in calm water, trusting the water to hold you, trusting the darkness to be safe, trusting that sleep will come when it's ready and that you'll be there to meet it, peaceful and prepared. There's nothing you need to do now, no problems to solve, no answers to chase, no puzzles to figure out. Just the calm certainty that mystery itself is a kind of lullaby, one that will carry you into sleep without effort or struggle. So let go now, completely and fully. Let your mind wander where it will, through dreams or darkness, through memories or nothing at all, wherever it needs to go. Thank you for spending this time with me, for letting me guide you through these theories, these questions, these mysteries about the universe we share. Thank you for your curiosity, for your willingness to wonder even as sleep approached, for choosing to end your day with learning rather than emptiness. It means something. This choice you've made, this decision to fill the space before sleep with knowledge and beauty rather than noise or worry. It says something about who you are, someone who seeks understanding even in the quiet moments before consciousness fades, someone who values curiosity and wonder, and I'm grateful to be part of your evening, part of your routine, part of the quiet ritual that carries you from waking into sleep, from questions into rest. You're not alone in this, you know. Right now, all across the world, others are listening too, drifting through these same theories, wondering these same questions, letting the same mysteries wash over them like gentle waves. Some are ahead of you, already deep in dreams, they're breathing slow and steady. Others are just beginning, just settling in, just starting their journey through cosmic wonder. but you're all connected by this shared experience, this common journey through mystery and curiosity, seeking rest and knowledge in the same breath, finding peace in questions that have no final answers. A quiet community of curious minds scattered across the planet, each alone in their bed but joined by wonder, by the desire to understand, by the choice to let learning be the last conscious act before sleep. Imagine yourself now, floating through the theories we've explored, passing by them as if through constellations in the night sky, each one a point of light in the darkness. Questions above, questions below, a galaxy of wonder all around you, and you at the quiet center, resting in the knowledge that mystery is not something to fear, but something to embrace, that not knowing is not failure but invitation, that the universe keeps secrets not to frustrate us but to keep us curious, to keep us reaching, to keep us human, to ensure there's always more to discover, always new questions to ask, always wonder waiting just beyond what we understand. Let that thought comfort you now, wrap around you like a blanket woven from starlight and uncertainty, soft and strange and somehow perfect. The theories we have explored tonight are just whispers in an infinite conversation, questions asked across time and space, mysteries that connect us to everyone who has ever looked up at the night sky and wondered why, how, what if. We're part of something larger than ourselves, part of humanity's long dialogue with existence, part of the universe's slow awakening to itself through conscious minds that can question and wonder and dream. There's nothing left to do now, no answers to chase, no puzzles to solve, no theories to understand or remember. Just the calm certainty that mystery itself is a kind of lullaby, one that will carry you into sleep without effort, without struggle, without needing anything from you except willingness to let go. So let go now, completely, fully. Let your mind wander where it will, through dreams or darkness, through memories or nothing at all, wherever it needs to go to find rest. Let your consciousness dim like a sunset, gradually, naturally, beautifully, colours fading from the sky as night arrives, the transition so smooth you barely notice it happening, awareness becoming dream, becoming nothing, becoming sleep, and know that when you wake, the theories will still be here, the questions will still wait, and the universe will still be strange and wonderful and full of mysteries worth exploring. But that's tomorrow's concern. Tonight is for rest, for dreams, for letting go of everything except the gentle pull of sleep. I hope you sleep well and dream softly. May your rest be deep, your dreams be gentle, and your tomorrow be bright. Thank you for being here, for listening, for wondering. Good night.